We're so glad to have Dr. Takaaki Kajita and a Nobel Laureate in 2015, and I'll let you have the honors of introducing you, Dr. Kajita. And I am Shanta Dixit, Director of Random School, and very pleased to have you. Namaste.
All right, I think we can now officially start, right? So thank you, Shanta ma'am, for your kind words, and to thank you, Ratu Bangla, for hosting this event on behalf of BCVSPIN. So I'm really pleased to see so many people here for the public part of our program. Whenever we have a public talk, we always worry that maybe the public is not so interested and we are putting in this effort in vain. But then every time I see all these people come in, and it tells me that I don't have to worry about these things. So it's a real pleasure to welcome you all to this event. Today we have a very distinguished guest amongst us, Professor Takaaki Kajita, who, as you probably have heard by now, won this prize called the Nobel Prize in Physics, which is no small feat, right? And before I introduce, before I invite him onto the stage, I would like to tell you a little bit about the program that brought him here and the program in the context of which we're organizing this event. So the story actually begins with another Nobel Prize. And this Nobel Prize was awarded back in 1979. It was won by Professor Abdus Salam. And Salam was from Pakistan. So when he won the Nobel Prize and became very prominent, he wanted to do something for this part of the world that he came from. And this is really the start of the BCVSPIN program. Back then there was no V, so it was called the BCSPIN program. And BCSPIN stands for Bangladesh, China, Sri Lanka, Pakistan, India, and Nepal. So this was the region of the world that Salam was targeting, and his goal was to really connect this region to the international physics community and really bring very renowned researchers from all over the world to this part of the world so that this community could interact with the global physics community. And the very first program under this BCSPIN flag actually took place in Nepal. Right? So this was a program that started back in 1989, and Nepal was the first host. And it was a grand success. And here are some pictures from this event. And Salam himself was there, of course, for the very first event and for several events afterwards. And there have been several editions of this BCVSPIN program, formerly BCSPIN program. And as you can see, it's traveled around South Asia, but also all over the world. And as you can also see, Nepal has actually been the strongest presence in terms of hosting this event. So Nepal was just this wonderful place that was very neutral in many ways, right? So it was close to travel for all these participants from these countries. It was also politically neutral, and people wanted to come and see the mountains and the culture in Nepal. And so for that reason, BCSPIN was very strongly tied to Nepal. It kept coming back to Nepal, and we have held several editions of this program. The most recent was in 2003, where we organized a two-week lecture, two-week summer school for students from South Asia. And so this happened last year in the summer, or just before the summer. And we had 66 students from all over South Asia attend this program. There were students from India, Nepal, Pakistan, Bangladesh, Sri Lanka, China, and Taiwan. And we had 12 distinguished lecturers from all over the world who came to Nepal for 2 weeks and made this program very successful. Here's a picture of the participants from this event last year. And some of you might remember that we also had a public lecture part of this program. And last year, our public speaker was Dr. Tracy Slatcher from MIT. And I think some of you were actually here for that lecture, and it was a great success. And that brings us to this edition of the BCVSPIN program. And this year, we have organized a conference that's actually going on right now. It's a one-week conference about particle physics and cosmology. So we have about 80 participants who are here from all over the world. There are 70 scientific talks that are being presented this week. So the program started today, and today was the first day. And so this public lecture will be part of this BCVSPIN conference program. And several of the participants at this conference are actually sat in the audience right now. So some of them are, if you look around, you might see unfamiliar faces, and they are actually scientists, very prominent scientists from all over the world who are here for a conference and also here for the public portion of this program. And so that brings me to the program we are here for. And we are here to listen to Dr. Takaaki Kajita tell us about this physics phenomenon called neutrino oscillations. And this was the thing that he won the Nobel Prize in physics for. And I won't tell you about the physics because that is what he's going to tell us about. So without further ado, I would like to invite Dr. Kajita up to the stage. Before I do that, actually, I would like to share one more picture. And this is just telling you that this is not the first time he was in Nepal. He was actually in Nepal for an earlier BCVSPIN conference. This was back in 1994 when, as you can see, he was a very young and energetic Japanese physicist who was here and spent a lot of time in Nepal. And we were very happy that after this, he went on to win the Nobel Prize in Physics and become a very popular figure. And we are even happier that after that, he still had the time and energy and enthusiasm to come back to Nepal and join us again for this 2024 edition of the BCVSPIN program. And so that brings us to the lecture by Professor Kajita. So please come on stage, and we'll be very eager to listen to you.
Well, good evening. Thank you very much for the introduction. Well, this evening, I want to talk about oscillating neutrinos. And, well, actually, this is the photo of the super Kamiokande experiment. And I have been working with this experiment. So today, I'm going to talk about the neutrino studies with this detector. And as introduced, I attended the BCSPIN school 30 years ago. And well, I had a great memory. Therefore, this time, I'm very happy to be back here in Kathmandu. In fact, 30 years ago, I came with my family. And actually, my son, when he came, was less than 1 year old. And during the stay, he had his first birthday. And this is the birthday cake with his name. Anyway, we had a great memory. Thank you very much. So today, I want to talk about neutrinos. And this is the outline. First, I want to briefly discuss what are neutrinos. Then, I want to move on the Kamiokande experiment. Actually, Kamiokande was the experiment before super Kamiokande. Then I want to move on to the super Kamiokande experiment and the discovery of neutrino oscillations. Then I'll probably briefly discuss the discovery of solar neutrino oscillations. Then before finishing this talk, I want to discuss neutrinos and the big mystery in the universe. And I'll summarize this talk. Okay, what are neutrinos? Well, almost 1 century ago, people were puzzled. I mean, physicists were puzzled with the beta decays. People observed that a nucleus emits an electron and convert it to other nucleus. And actually, if this is true, then you can calculate the energy of the electrons emitted. So we expect that the electron energy is a unique value. But if people observe the electron energy, people found that the electron energy has a continuous spectrum rather than a unique value. So people are really puzzled. Then, on December 4th, 1930, Pauli wrote a letter to Dear Radioactive Ladies and Gentlemen. Actually, this tells us, not serious. Well, this was a letter to the conference people. And well, he was unable to attend the conference because he had to go to a dance party. Anyway, he wrote, I have hit upon a desperate remedy to save the law of conservation of energy, namely the possibility that there could exist in a nuclei electrically neutral particles. What he said was, if a nucleus emits an electron, at the same time, a neutral particle is emitted. And therefore, the electron energy cannot be a unique value. So this way, he thought, naturally explain the continuous energy spectrum of electrons. So this was the idea. After that, of course, people get more serious about this idea. And in fact, in the 1950s, people observed electrons for the first time. Observed neutrinos for the first time. After that, there have been many, many, many studies of neutrinos. And nowadays, we know a lot about neutrinos. And if I summarize what we know about neutrinos in one page, maybe this is like this. Neutrinos are fundamental particles like electrons and quarks. And neutrinos are something like electrons, but without electric charge. Well, you know, in the atom, at the center, there is a nucleus, and electrons are surrounding. Well, actually, nucleus has positively charged, and electron has negative charge, and therefore, they attract each other. This is the way to form an atom. But neutrinos have no charge. Therefore, if a neutrino comes close to a, say, nucleus, the neutrino doesn't feel any force. So neutrinos just go straight. Therefore, neutrinos can easily pass through even the Earth. But fortunately, neutrinos can interact with matter very rarely. But anyway, because of this, we can study neutrinos. And neutrinos have three types, namely electron neutrinos, muon neutrinos, and tau neutrinos. And finally, I want to say that neutrinos have been assumed to have no mass. Okay, that are the basic summary of neutrinos. Now, I said we can study neutrinos. How can we study neutrinos? Well, we can never see neutrinos themselves. Then what shall we do? As I said, neutrinos very rarely interact with matter, with the nucleus. So if a neutrino interacts with a nucleus, a typically charged particle is emitted. And we have various ways to observe these charged particles. For example, if this nucleus is a water nucleus, say oxygen, then this charged particle propagates in the water. Then at the time, this particle emits light or photons. And of course, we have various ways to observe light. If we have photodetector, then we can observe this light. So this way, it is possible to observe an interaction of neutrinos. And this way, we study neutrinos. Now, I want to move on to the Kamiokande experiment. Actually, the initial name of the Kamiokande was Kamioka nucleon decay experiment. And I want to tell you the story. In the 1970s, about 50 years ago, new theories of elementary particles appeared, and these theories predicted that protons should decay with a lifetime of about 10 to 30 years. Well, 10 to 30 years is a very long time. Our lifetime is about 10 to 100 years. And the present age of the universe is approximately 10 billion years. So compared with the age of the universe, the predicted lifetime of proton was much, much, much longer. So that means if proton decays, our life may not change at all. But scientifically, this was a very important prediction. Therefore, several proton decay experiments began in the early 80s, and one of them was the Kamiokande experiment. And Kamiokande was located in the central area of Japan, in the mountainside. And Kamiokande was, as shown here, it was a 3,000-ton water detector. It had about 16 meters in diameter and 60 meters high. And well, inside this tank, there are many water molecules. Therefore, there are many protons. Therefore, if we observe inside of the Kamiokande tank, one of the protons may decay at a time. Therefore, we wanted to observe proton decay this way. And I was fascinated by the concept of proton decay and participated in Kamiokande. At the time, I became a graduate course student. That was April 1981. Well, okay, so this was the idea. Then next thing is to construct the detector. We cannot buy this kind of detector, so we have to build. And so in the spring of 1983, we come to the experimental site and worked together. So this photo was taken in the spring of 1983 when we constructed the Kamiokande detector. Well, maybe the image of the scientist is slightly different from the people in this photo. We had the safety hat, rubber boots, and working wears. Anyway, after taking this photo, we came into the mine deep underground to construct a detector. By the way, in the middle, in front, you see a gentleman. This is Professor Koshiba. Actually, he received Nobel Prize in Physics in 2002 by the observation of neutrinos in Kamiokande. Anyway, after this photo, we came into deep underground and constructed the Kamiokande detector. And this photo shows the construction of the Kamiokande detector. As I said, Kamiokande had 60-meter high, and we needed to install the photo detectors into the inner wall of the detector or tank. So the first question was how we install the photodetectors into the wall of 16-meter high. Well, we had discussions, and finally, we decided to use these plastic boards. We installed the photodetectors in a day, just one row. Then we raised the water level 1 meter. Then we put another layer of photomultiplier tubes, photodetectors. So we thought this is a safe way of installing the photodetectors into the detector. In fact, even if you drop from the boat, you may not die. And in fact, during the construction, no one dropped from the boat. So that was successful. And in fact, I enjoyed these works very much. Also, I was excited because I thought that the data from Kamiokande may contribute to physics much. And around that time, well, that was the first year in the PhD course, I decided to become a physicist. Okay, so our construction of the detector was successful, and we started the experiment in July 1983. And of course, we wanted to observe many proton decays. But unfortunately, real proton lifetime was much longer. So we were unable to observe proton decays. Instead, we observed background events to the search for proton decays that are neutrinos. And these neutrinos are created in the atmosphere of the Earth. Well, there are cosmic rays. Well, cosmic rays are high energy particles coming from the universe somewhere, we do not know. And these cosmic rays, once come into the atmosphere of the Earth, they interact with air nucleus. Then typically, pions are produced, but pions are unstable, decay to other particles. And during this decay chain, neutrinos are created. And of course, as I said at the beginning, most of these neutrinos simply pass through the Earth. But some of them, very rarely, interact in the Kamiokande detector. And that was the background to the search for proton decays. So our life was much easier if there were no neutrinos. But anyway, this is a reality. There are neutrinos. Now, I want to talk about our studies around 1986. Well, already 3 years passed since the beginning of the Kamiokande experiment. We had no evidence for proton decays, but we still wanted to observe proton decays. And in fact, at that time, we have already accumulated a substantial number of neutrino background events. Therefore, we better separate the neutrino background from the proton decay signal. And to do so, I developed a new software to improve the proton decay analysis. Of course, if you write a new software, you have to check this software as much as you can. There are many problems always. So as a test of the new software, the neutrino type, that means electron neutrino or muon neutrino, was studied for the atmospheric neutrino events. Then we found that the number of muon neutrino events was much fewer than expected. Of course, this was a test of the software, and software told us something unexpected. Then, of course, in most cases, this is the problem of the software. We have to find out where is the problem. So we thought that it's very likely that there are some mistakes somewhere in the data analysis, and we started various studies to find out mistakes. Well, around that time, I think we had a lot of time. We studied for about a year to find out the software mistake. But even after 1 year, we were unable to find out any problem. So we concluded that the missing muon neutrino events cannot be due to any major problem in the data analysis. Then at that time, we thought maybe we should report our strange data to the community. So we wrote a paper. Actually, the paper we wrote was quite, in a sense, quite simple. We reported the number of muon neutrino events observed and compared with the simulation, that is the expectation. And well, as shown here, the number of observed muon neutrino events was much fewer than expected. And at the same time, we counted the number of electron neutrino events and compared with the expectation. Then, in this case, the number of observation and the expectation essentially agreed. That's all we wrote. We simply wrote the number of events we measured. Well, that's all, but well, although we had no clear idea what was the cause of the missing neutrinos, I was most excited with the data. There must be some reason for this data. So I changed my research completely from the proton decay searches to neutrino studies to know what are going on in neutrinos. Okay, that was actually a paper published in 1988. Well, for a while, there were no supporting data from the other experiments. And finally, in 1991 and 1992, there was a supporting data coming from the IMB experiment. That was another large water Cherenkov detector. So they reported essentially the same result as Kamiokande. And actually, I was very happy to know this result. But still, we had no clear idea what was this neutrino still propagate to the right, then that neutrino type come back to muon neutrino, then tau neutrino, and so on. So this is neutrino oscillations. And if this is happening, then we thought we can naturally explain the data. But, well, of course, this was just one of the possibilities. Therefore, we needed to understood better. Anyway, well, I want to come back to 30 years ago. Well, in 1994, BCVSPIN school in Kathmandu I discussed this problem. Also, actually, I discussed solar neutrino problem as well. Anyway, I think that was a very interesting time. Now, as I said, neutrino oscillation was a possibility to explain the data. But we wanted to make sure that neutrino oscillation was a real solution to this problem. So we thought this way. As I said, neutrinos are created in the atmosphere of the Earth. Then some of the neutrinos are created above us, typically 10 to 20 kilometers above us. And these neutrinos come to the detector after traveling 10 to 20 kilometers. Well, maybe 10 to 20 kilometers could be short for these neutrinos. Then these neutrinos may have no time to change their type. Now, at the same time, neutrinos are created in the other side of the Earth. And these neutrinos come to the detector after traveling a very long distance in the Earth, typically 10,000 kilometers. So they have to travel really a long distance. Then maybe these neutrinos might have enough time to change their type. So we thought this could be happening. And well, in other words, we thought an asymmetry of the up versus down-going flux of mu neutrinos should be observed. However, we realized Kamiokande 3,000-ton detector was too small. The number of neutrino events we could observe was really limited. And therefore, we needed a much larger detector, and that was Super Kamiokande. Now, I'd like to move on to the Super Kamiokande experiment and the discovery of neutrino oscillations. Well, here is the explanation of the Super Kamiokande detector. It is a large detector. It has about 40 meters in diameter and 40 meters high, and it contains 50,000 tons of very, very clean water. And this photo shows the inside of the Super Kamiokande. And if you look at this photo carefully, there are 3 people on the plastic boat. So then you realize how big the detector is. By the way, Super Kamiokande is an international collaboration. At present, we have about 230 collaborators from these countries. Well, anyway, even in Super Kamiokande, we physicists had to work to construct a detector. And this photo was taken in the spring of 1995. Every day, this number of people come into underground for constructing the detector. And this construction work continued for about a year. And finally, in April 96, the Super Kamiokande experiment started. Well, of course, we knew, before starting the Super Kamiokande experiment, we knew that neutrinos are interesting. Therefore, from the beginning of the Super Kamiokande experiment, we worked very hard to understand atmospheric neutrinos. And in fact, after 2 years from the start of the experiment, we were able to report our first significant result at the neutrino conference. And well, here I copied one of the slides we presented at that conference. By the way, today I'm giving this talk using PowerPoint, but in the 20th century, we didn't have PowerPoint. So we had a different technology. We had a plastic film, and we copied the data, histogram, and then we wrote down several comments to the plastic. And this plastic was projected to the screen. So, well, 25 years ago, the technology was completely different. Anyway, there's a reason that I showed this view graph. This view graph was very important. Well, let me explain a little bit more. So the horizontal axis is the neutrino arrival direction. 1 means downgoing neutrinos, and -1 means upward-going neutrinos. These neutrinos came from the other side of the Earth. They traveled a very long distance. Then please look at the lower panel. That is for muon neutrinos. The black circles with error bars show the data, and the hatched histograms show the expectation. And in the expectation, there's no neutrino oscillation. Anyway, from this histogram, you find for downgoing neutrinos, the data and the expectation agreed quite well. On the other hand, for upward-going neutrinos, the number of observed data was essentially half of the expectation. What does this mean? Of course, this data can be explained very well if we assume neutrino oscillations. Neutrinos coming from the other side of the Earth change their type while propagating in the Earth. Therefore, when they come to the super Kamiokande detector, the probability that muon neutrino remain as muon neutrinos is only 50%. That is the data told us. So this way, we were able to convince the global neutrino community that neutrinos change their type. And that means neutrinos have very small mass. Well, I think we were able to convince the neutrino community with essentially with this data. Then something unexpected happened. The US president at that time was Clinton, and he gave a talk at MIT's 98 commencement. Well, this is a copy of the YouTube, but well, actually this is Clinton's talk. And in the middle of his talk, he mentioned about the discovery of neutrino oscillations. Let me simply read what he said. Just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, that may not mean much to most Americans, but it may change our most fundamental theories, from the nature of the smallest subatomic particles to how the universe itself works, and indeed how it expands. Of course, as the US president, he mentioned that in Super Kamiokande, there are many, or significant number of US physicists working. Then he came back and said, continued, the larger issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. I think we were really honored to hear this kind of remark from the US president on the next day of the discovery announcement. And I am hoping that all the US presidents are like this. Okay, now I want to move on to the next topic. That is the discovery of solar neutrino oscillations. Well, certainly the topic is completely different. Well, there was a problem called solar neutrino problem. The sun generates energy by nuclear fusion processes, and neutrinos are created by these reactions. Therefore, the observation of solar neutrinos is very important to understand the energy generation mechanism in the sun. Therefore, the first solar neutrino experiment that detected solar neutrinos were carried out in deep underground. And Homestake experiment observed solar neutrinos for the first time in the late 1960s. However, there was a problem. The observed event rate was only about 1/3 of the prediction. So this was the solar neutrino problem. And in fact, during the 20th century, several other experiments, including Kamiokande, successfully observed solar neutrinos. But all of these experiments found the missing solar neutrinos. But unfortunately, during the 20th century, we couldn't understand what was the cause of the problem. Then the experiment that contributed really significantly to understand the problem was the snow experiment. It is another solar neutrino experiment, and actually it was located very, very deep underground, 2 kilometers from the surface. And it contained 1,000 tons of heavy water, D2O. Well, actually, using heavy water is not, that means the experiment is not cheap. I don't know the present price for the heavy water, but please check. This is not cheap experiment. Anyway, heavy water was the key. Using heavy water, the snow experiment was able to observe the total neutrino flux coming to the Earth, independent of the neutrino type. In fact, they found the total neutrino flux, independent of the neutrino type, was just consistent with the theory prediction. But this experiment is also able to observe electron neutrinos coming from the sun. Actually, they found the number of electron neutrinos they observed was only about 30% of the prediction. So that means about 70% of the flux are mu neutrino or tau neutrino. And since the sun can only generate electron neutrinos, this was the evidence for neutrino oscillations, solar neutrino oscillations. So this way, early in this century, we understood that the missing solar neutrino problem was due to neutrino oscillations. And of course, we were excited to hear this result. And well, actually, all the neutrino physics community was excited. And there have been many neutrino oscillation experiments. Well, here is the partial list of the neutrino oscillation experiments that contributed to our understanding of neutrinos. So you find there are many experiments. So we are really excited. But you may wonder, why neutrino physicists were so excited with the neutrino mass? Well, of course, electrons have mass. Quarks have mass. Then, in a sense, it's very natural that neutrinos have mass. Why we are so excited? Well, let me tell you, we are really excited. Well, here I show the mass of elementary particles. Well, of course, electrons have mass, and there are similar particles like electrons, but different, muon and tau. The mass of these particles are shown by red colors, and other particles are quarks. There are 6 types of quarks, and their mass are shown by green and blue colors. Oh, by the way, horizontal axis is the mass. Now, in the last 25 years or so, sorry, as I said, neutrino physicists have been working very hard to understand the neutrino mass. And I think now we understood the neutrino mass rather well. And let me plot the neutrino mass here. The neutrino mass are like this. So you find that the neutrino mass are plotted in a different place in this plot. And well, you must be careful about the horizontal axis. Here, 1 unit is 100. Then you can simply count, and you can easily find that neutrino mass is approximately, or maybe more than, 10 billion times smaller than the corresponding mass of quarks and charged leptons. 10 billion times smaller. Very, very, very small. And we believe that this is the key to better understand elementary particles and the universe. And therefore, we are excited. And of course, if we understand why neutrino mass are so small, we are sure that we understand elementary particles better. But we think we understand the universe better by understanding neutrinos better. Why? Well, let me show this photo. This is the photo of the far universe. We see many galaxies. And there's one thing we know for sure. These galaxies are all made of matter. There's no antimatter galaxy. Well, of course, that is kind of trivial. However, if we think about the history of the universe, we find this conclusion is non-trivial. We know the universe began with Big Bang. The Big Bang universe was very hot. And in this very hot universe, always particles and antiparticles are created simultaneously. That means number of matter particles and antimatter particles should have been the same. Then, with the universe cooled down, no more particle and antimatter particle creation. Instead, particle and antiparticles meet and annihilate, disappear. So then what will be the present universe? There should be no matter particle remain, no antimatter particle remain. So the universe should have nothing. But of course, we know there are matter particles. We know we exist. This is actually a mystery. We don't know why. But, well, there's an interesting idea, just an idea. Well, neutrinos with very small mass might be the key to understand the big mystery of the matter in the universe. So, well, this is still an idea. Therefore, we would like to check if this idea is good or not. So, we still have to study neutrinos. In fact, we'd like to know if neutrinos are related to the origin of the matter in the universe. And for this, as the first step, we would like to observe if neutrino oscillations of neutrinos and those of antineutrinos are different. I'm sorry, maybe some of you got confused what I'm talking about. But anyway, this is what we'd like to observe. And unfortunately, we found that the present generation of experiments are not powerful enough to study this effect, this difference. Therefore, we need the next generation of neutrino experiments. And in fact, there are two very large projects are going on under construction, one in United States and one in Japan. Well, of course, I don't want to go into details of these experiments, but let me just as an example, tell you about the project going on in Japan. Well, as I said, the present generation of experiments is not powerful enough. Therefore, we need larger neutrino detector than Super Kamiokande. So the next generation of experiment is called Hyper Kamiokande. It will have about 70 meters in diameter and 70 meters high, huge underground detector. So with this huge experiment, there should be many important research topics in neutrino physics and astrophysics. And as shown in this photograph, at this moment, we are just excavating a very large underground cavern. And the experiment is scheduled to start in 2027. And also I want to mention that this is a very large international collaboration. At present, there are about 600 collaborators from 22 countries. So in a few years, a new round of neutrino studies will begin. Okay, let me summarize. As I said today, neutrino oscillations were discovered by large underground detectors, and the discovery of neutrino oscillations opened a window to study physics beyond the present understanding of particle physics. And neutrinos with small mass might also be the key to understand the fundamental questions of the universe. So I think it's fair to say that neutrinos might be the key particles for the understanding of the smallest particles and the largest universe. And I hope that I convinced you that science is really exciting, and I hope that young people, you become scientists. Okay, that's all from me. Thank you very much.
Yeah, thank you so much for that amazing talk. No problem. Yeah, so thank you so much for that amazing talk. I'd like to repeat what you said, that these are not just physics results, right? These are really incredible moments in the history of our societies and us as humanity that really highlight our place in time and our relation to the universe. And we are so thankful to you that thanks to you, we got a personal insight into one of these milestone events in human history, essentially. And I hope everybody will take that at heart and really appreciate what an amazing thing you've just heard about. And with that, I think we have a few minutes to ask him some questions you might have about this talk or about anything else. Please raise your hands if you have any questions, and we will find you.
Thank you for the amazing talk. My first question was going to be about, you mentioned how neutrinos have mass. I was wondering if their mass comes from the Higgs mechanism, and I was also wondering, the fact that neutrinos have mass lead to new physics. What does this new physics look like? Are we expecting a fourth generation of neutrinos, not just the three as predicted by the standard model? Maybe, I don't know, I've heard of sterile neutrinos, or like, where do they come into the picture?
Okay, thank you. Thank you for this question. Well, to be honest, we do not know the answer yet. But generally, we think that neutrino mass are generated by different mechanism than Higgs mechanism. If the Higgs mechanism is the mechanism to generate the neutrino mass, we do not understand why neutrino mass is so small. This kind of fine-tuning of the mechanism is very unnatural. Therefore, we think there should be some other mechanism to generate a very small neutrino mass.
Lecture. I actually have two questions. The first one being, since as mentioned in the lecture, you said that the cosmic rays interact with the A nucleus to form the new neutrinos, right? But our issues is very focused underground. Why is that? So, like, since the neutrinos are mostly formed in the atmosphere, why aren't our issues focused in the atmospheric level? And the second question.
Oh, sorry. About the first question, your question is why we go underground? Yeah. Well, let me answer before forgetting about the first question. Well, okay, thank you. As I said, neutrino interactions are very rare. Even in Super Kamiokande, 50,000-ton detector, the atmospheric neutrino event is about, say, I already forgot the exact number, but less than 10 events per day. On the other hand, there are backgrounds cosmic ray background is very serious. Even in 1,000 meter deep underground, cosmic ray event rate is 2 events per second. So we have to reduce these cosmic rays as much as possible. But of course, there must be some limit. Therefore, there must be some limit by the data analysis. Therefore, we go deep underground. If we go deep underground, we have less cosmic ray flux. That is the reason.
Thank you. Maybe we will have to develop a new technology for the atmospheric level research. All right, with the second question being, since the research are going on regarding the mass of the neutrinos, but with regards to the charge, I think, as per my knowledge, maybe insignificant, the neutrinos are assumed to be electrically neutral, but antiparticles are often defined to have opposite charges, and some of the properties opposite. How do we actually differentiate between the neutrinos and the antineutrinos?
Yeah, that is a fundamentally important question. Indeed, that is a fundamentally important question. And well, at present, we do not know the answer. In the future, we are hoping that, we understand that neutrinos are indeed fundamentally different because of this neutral charge particle.
More questions? As you can see, we have some very young and talented scientists in the audience.
Yeah.
I was wondering, how does the difference in the oscillation of neutrino and the antineutrino explain the asymmetry of particles and antiparticles in our universe?
Thank you very much. Oh, okay, this is very complicated. If we observe the difference between oscillation of neutrinos and oscillation of antineutrinos, that means there is a symmetry breaking called CP vibration. And well, we know that CP vibration is needed to generate the baryon asymmetry in the universe. Then, of course, if you go into the actual model, it takes many minutes.
You'll have to get a PhD in physics.
Professor, does neutrino striking nucleus have any effect on the atom?
Say again, I'm sorry.
Does neutrino striking at nucleus have any effect on atoms?
Neutrinos striking the
Pardon me, may I rephrase the question a bit? When the neutrino strikes the nucleus, does that bring any significant difference or effect to the atom itself or the nucleus itself?
Oh, thank you. Okay, thank you. Well, okay, yeah. Well, let me answer this way. As I said, if a neutrino interacts with a nucleus, then a charged particle is emitted. Well, of course, the total electric charge must be conserved. That means the nucleus, after the interaction, should be some other nucleus. And therefore, the atom should be a different atom. Okay?
More questions?
You mentioned that out of the expected results, 50% of the neutrinos weren't detected, right? Because they oscillated and they changed flavors, right? So I was wondering, what are the requirements for neutrinos to oscillate? Like, what requirements do they meet to make them oscillate?
Oh, okay. What is the requirement for neutrinos to oscillate? Yeah, okay, thank you. Well, the first requirement is neutrinos should have mass. If neutrinos are massless, then neutrinos can never change their type. In addition, well, of course, if we go into the details of the, well, not very much detail, but go into physics, there is another requirement that there must be a mixing between the mass state and the neutrino flavor state. Well, okay, I'm afraid I cannot explain this very well, sorry.
Again, that's a good reason for you to come up with this.
Namaste. Thank you for a very exciting, interesting talk. I'm not a physicist, I'm a physician, so a lot of what it was what we call a supracortical, but it's very interesting. I wanted to ask, so when you have to design these experiments, these sites, these huge labs, that would cost probably billions and billions. And how do you go about convincing the governments or the authorities funding agencies? Do you do those types of
Yeah. Okay, thank you very much. Well, certainly, I think we were fortunate that our government was convinced to construct these detectors. And well, also I think this largely depends on the history. Well, when the first Kamiokande experiment was constructed, well, actually, I am not sure how much the government was involved. Well, to some extent, the government was involved, but people, collaborators, tried to get money from various sources, then constructed the detector. Then the Kamiokande was, in fact, very, very successful. Kamiokande observed supernova neutrinos for the first time, and Kamiokande found neutrino problems. And therefore, we were able to convince the Japanese government that this is going to be a very important experiment, and you have to pay for this experiment. That's what we try to convince.
Wasn't the original Kamiokande intended to absorb proton decays? So that's why they used water in there, so they could absorb the nucleus decay. But eventually, why did that be useful for the neutrino detection as well, the water in the tank?
Sorry, what is the
The water was originally intended for observing proton decays, but later on they found out they can observe neutrinos. So why did they continue using water?
Oh, thank you. Yes, okay. Why we continue use water? That is an important question. Well, we have to think about the money. Water is free. In addition, actually, we don't have a big reason to change the medium because, well, in order to observe light or Cherenkov light, the material must be very, very transparent. But, well, we do not find any other material that is very, very transparent. Well, air is a possibility, but in case of air, the total mass should be very small. Then, in this case, the number of neutrino interactions should be very small. That is a problem.
I really enjoyed your lecture. I had a question. Do these neutrino oscillations follow some sort of pattern Like, how often do they oscillate, or do they follow some sort of pattern, and can we like predict whether an electron neutrino is going to oscillate to a tau or a muon neutrino, or is it something quantum mechanical where we don't know until it's actually like measured?
Okay, well, yeah, this part I didn't tell at all, certainly. Well, depending on the mass of the neutrinos and depending on the energy of the neutrino, then you can calculate the length to change their type. And well, about the solar neutrino case, actually, if they propagate in the vacuum, they need much longer distance to change their type compared with the neutrinos created in the atmosphere.
Could you please explain those symmetric variations apart from CP variation? Could they explain disproportionately higher amount of matter remaining in the universe? And other symmetry variations significant in the early universe?
Okay, you want to know the mechanism about the matter symmetry in the universe? Okay, yeah, okay. Let me try. Okay, as I answered to some question, in order to generate a very small neutrino mass, we may need some new physics. And one of the ideas is to assume that there exists a very heavy neutrino-like particle. Okay, anyway, this is the idea. Well, okay, anyway, this very heavy neutrino-like particle should have existed in the Big Bang universe. And this very heavy neutral particle, of course, should decay immediately. But if there is CP violation, this could generate the source for the matter asymmetry in the present-day universe. If I make the story very short, then it is like this.
Yeah, so I think there are quite a few questions left, I'm sure. But unfortunately, I think now we have to close the question and answer session for many reasons. One is that the good people who have to close the auditorium and go home really need to do that at some point. The other is that for the conference participants, BCVSPIN participants who are here, there's a bus waiting for you to go back to your rooms. And for that, you will need to follow Cyril or the other conference volunteers as soon as the program is over. And in about 5 or 10 minutes, the bus will take you back. So when the program ends in the exit, please make sure you follow them and go back to the right place. But the most important thing that we have to do is to really offer our gratitude to Professor Kajita for taking his time to be here.
Thank you.
And it's really a truly wonderful event. So thank you all for coming as well. And you don't know this, but this is not the first talk he's giving today. So in the morning, he also gave a conference talk, a very technical talk at the conference. And I think the questions you're getting now are much more difficult than the ones in the morning. So really, thank you all for asking those questions. But really, to come back to the main point, we would really like to thank you. And as a token of appreciation, we have a small gift for you on behalf of the BCVSPIN program. And I guess on behalf of all the people.
Oh, thank you. Yeah, okay.
Yeah, so
we're good.
We're good.
Yeah, thank you.
Yeah, thank you very much. Presented by Rich Rath, who is the chair of the organizing committee for the conference that we're organizing. He's a professor of physics at St. Mary's College in the US. And I'm particularly happy that you're getting this because before this talk, we were just walking around in Passover Square and he was really fascinated by the designs on all the windows we were looking at. So now you have a little piece of Nepali. We wish you a good night. Thank you.
Mesmerizing as
So for the
usual.
BCVSPIN
Thank you,
people
sir.
who
Thank
want
you.
to go back, of course, follow
And
the
I shall
volunteers.
safe travel back tomorrow.
Oh, yeah, thank you.
Yeah.